Hey guys, welcome to the next channel. So this is my follow-up video of my couple of videos which I shot in this title. So in case if you haven't watched them yet, you can watch the same over here. So this is my first episode on this title. So in this I have given a basic introduction and also shown a sample demo code with which you can analyze the total overhead of socket communication. In case if you use sockets as IPC, the amount of overhead involved in the case of sockets. So eventually the packets, in case if this IPC is involved within the same system, the packets have to go from user space to the kernel space and then kernel space to the user space back to the user space through the socket subsystem and as well as through the entire IPv4 stack. And in this case I am using UDP sockets because I can't use we can't test these kind of parameters like with something like TCP, because it should be some kind of discrete communication. So in this case we need to choose UDP. So this is the reason I'm doing the same. So in case if you watch my couple of episodes, you will get the entire big picture. So in both the episodes I have done in the second episode I have done a variant of the first episode code, and then I have done also a demo on various devices, and in a way I have benchmarked the performance in various devices. Whereas in this episode I have done a message queue. The entire same code I have implemented or put on, or the logic I have put on message queues, so that we can test and compare the overhead of socket subsystem versus something like message queues. So this I have taken a very simple message queues. Let's not get into very much depth about the various variants of message queues and stuff like that. It's a very simple. So this is my code. I have written message queue send.c and receive.c, as you can see here, and like I do in all my episodes, I'm going to share this code as well, so that you can download and then you can change, and in case if you are interested you can benchmark your device as well. So, and this is my previous episode code, so we can compare the performance once with this and then the performance with this new approaches. So you can see here it's just the same as the previous episode, which is video ID 227. So you can see here this is 227. So you can see here this is the code. So effectively we are sending a huge data in the form of buffer from a UDP client to the UDP server, and then we are just pumping the packets. So this is what you must have seen in the previous episode. So in this case what I'm doing is I'm taking a maximum buffer of around you can see here it is around 10 KB. Whereas in this case what is happening is I'm unable to give 10 KB, maybe due to some restriction with the message queues, I'm not sure, because I'm not extensively ever used message queues. I just used very long ago and then again I discarded. The fact I love sockets as a part of IPC is it is very easy to debug, and it is also easy to debug as a part of your Wireshark capture and stuff like that. And also you can able to make sockets work within multiple systems in case suddenly it demands a multi-device networking application and stuff like that. So this is the advantage of using sockets. So as you can see here the code is fairly simple. So in this case we are doing a message queue receive and then a message queue send, and just like UDP socket client and UDP socket server, in the case of send you can assume it is like UDP socket client. Its job is to just pump the data from this UDP the message queue buffer in one point to the other receiving end of message queue. So you can see here it is fairly simple, and this I'm unable to extend the same. As I said earlier, I'm not sure why it is happening, and this is the max I can reach. Initially it has stopped working when I gave around the same size as this max buff. So I can arrive at a point somewhat like this 8024 and here up there. So beyond this it is just stopped working. Maybe I need to check the specs in case if it has any limitations, or else it has any control parameters in the kernel space where I can change to extend this size. So I need to explore the same. So this doesn't justify, or this doesn't just make any justice, because we have to compare with the same amount of max buff to eventually benchmark it as good as possible. So anyway, you can settle down for now with this. So you can see here, this is my message queue buffer, and it has this message queue type and buffer, and I'm passing this max buff. And inside the code, so once it initializes, I'm just creating this message queue, and then I'm doing a memset of the buffer's data. I'm just doing a memset with characters like AB, in case if you need to read in the receiving end, and then in case you need to check the integrity of the same, you can do the same. So it is just purely optional. So I just want to recreate the same thing what I have done earlier with my UDP socket code as well. So this is the reason I'm just doing the same, and then followed by which you can see it has an infinite while loop. So with this, it is going to pump this data. So the receiving end, it is fairly again simple. You can see here it is having the same similar code, and then below after this, you can see here it has this infinite while loop, and it has the same copy paste logic of what I have done in this UTP server as well. So it is doing the same thing, and you can see here it is just getting this diff of timestamp, and then once the diff is more than that whatever we need, like in a second how much data is captured in a second, we are just dumping on the screen. So this way we can compare this specific approach versus this older approach, and then we can benchmark. So in the older approach, you must have seen I have done also something different. Let me just hold this against the camera. So in my older demo, so what I have done is, you have this UDP client and then UDP server. So hope the camera is able to focus the same. So in this case, what I have done is I have pumped in this way, and then once we have benchmarked with one instance, I created also some couple of instances, and I have done some sort of simultaneous pumping of data to analyze what is the maximum extent it can support the same. So in this case, it is a sort of parallel operation, whereas in this case eventually it is all going to get serialized. It is going to get one packet or one data buffer after another data buffer, so as the way it reaches this UDP server, listening server. In the case of message queues, the objective is not something like this. The objective is, what we can do is, we can create the receive instance recv, because we should not call this as a server. So we have this receiving instance, and then we have this send. So what we can do is, in this case we can send the same way. So effectively this entire thing is going to be supported in the kernel space, the data, because we should not call this as packets. The data have to go from user space to the kernel space, and then through the whatever message queue subsystem, it is going to get passed, and then it is going to be received in this receiving instance. So this is what effectively is going to happen. So this is what fairly we are going to test. In this test of this episode, I am going to do a single instance versus a single instance of message queue versus a single instance of UDP sockets. So this way we can see how much is sockets subsystem, especially like with IPv4, is adding overheads on the same assets, versus without that is what you get something like message queues in a form of IPC. So with the message queues, as one can understand, we can't extend it with multiple systems and stuff like that, and that's where again you need to use networking layer, so that you get IPC spanned across multiple systems. So let's just compile the same, and then we can test the performance between both. So you can see here I have just compiled both of them even before starting this video. So let us just open another couple of tabs, and then we can do a test message queue send, and then you can start an instance message queue receive. So you can see here it is getting around with one instance it is getting around 7.5 Mbps. So this is bytes per second. So this is getting around 7000 to 7.5 megabytes per second. So let me grab a calculator. So we can take an average like let's take an average like 7.2 because it is showing 7 to 74 and stuff like that. So we can take an average of around 7200 or 7300. So let's take an average of 7200 into 8, which is like 57,600. So this is like around 55 to 56 Gbps of speed. So it's cool compared to what you can see with a single instance of UDP sockets. So let us just stop this test, and we can once again do the previous episodes test, and then we can compare both. So this is around so let me mark on this sheet. So this is around 57,600. So divided by 1000, you get like 57 or 56 gigabits per second. So let us write it as 56 Gbps. So hope you can see here. Let us just stop this, and then we can run the previous episodes sample code. I believe it is around 3.5 or 4,000 bytes per second. So we can stop the same, and we can go back here, and let us go to this folder, to done, cd done, cd 227, cd done 227. Yeah, and let me just run UDP socket server and then UDP socket client. So hope you can see here it is showing around 4024 megabytes per second. So it is on an average of 4000 megabytes per second. So let us just do a conversion of the same. So 4000 into 8, which is 32,000 bits per second. So divided by 1000, it can be around 31.5 or 32 Gbps. So let us just write the same. So this is around 32 Gbps on this system as well. So in case if you take the same code and if you run it on your laptop or Raspberry Pi or something like that, you get a different measure, and this is where you can benchmark your overall system's performance as well with this technique. So this is the overall objective of this entire series of videos which I have discussed in the first episode. So you can take the same code and you can run it on your laptop, and you can find the difference between what it can do versus what better system, in case if you have a quad core system or a 6 core PC or a gaming PC, you can test the performance between the both of these devices. So you can see here it is a huge marginal difference. In case if you are interested, you can also run multiple instances of message queues so that you can get the kind of breaking point or some kind of threshold at which the maximum possible data transfer is possible with sockets, as I did it in the episode 2 versus in this episode with message queues alone. So you can do that way. So let us just do a diff. It is around 56 gigabits per second versus 32 gigabits per second. So if you run 32 divided by 56, so star 100, so we get a boost of around 57 percentage, and on an average you can consider that's a boost of around 50 percentage. It's almost the double speed. So it's almost a double speed. I'm not saying it's the double speed of that. So this is the amount of computational power we are losing in the form of socket subsystem in case if you need an IPC within the same system. So this is an interesting research, and in case if you are interested, you can do it on multiple devices. Especially I'm more interested in case if users are doing it on in IoT devices, not just the traditional x86 laptops. So this is very interesting because IoT devices are less featureless, limited resource, and it is going to give an interesting significant data analysis, and we can do some kind of real-time benchmarking this way. It's just not CPU benchmarks which will give you anything. This is the real benchmarking you can do on a system and then figure it out what is your device is capable of. So the more cores you have, the more instances you can run, and this is what I have demonstrated in the earlier episode as well. So, and whereas in case if you are limited by CPU cores, and maybe even a single core having more computational performance power, in that case you get more performance with just single instance. So it depends on what is the core level performance of each core in your CPU versus you may have like 20 cores or 30 cores like a Xeon processor, but each core level performance is limited, so it can be any combination of this. So hope you guys have learned something in this episode. In case if you have any questions and in case if you have any suggestions, you can communicate through YouTube comments, and you can also post an email and participate in discussion forums as well. So as I do with all my episodes, I'm going to share this code as well in Google Drive, and I'm going to give the link in the video description so that you can download the same and you can test it as well, and as well as in case if you are interested, you can also download my couple of previous episodes sample code as well. So hope you guys loved watching this video. Thank you. Have a nice day. Bye bye.